In this video, we'll go through the two scenarios where firstly the ball is released from rest and then it bounces off from the ground. And the other scenario is when you throw a ball up, it goes vertically up to the highest point and then it falls back to your hand. And this kind of question is very common and you should know that it has come up for is a common kind of question, and these are just examples of pure physics. All right, this is a ball that is released from rest, okay, thrown up. You're supposed to sketch the velocity time graph, and this is another example. And all this so far is without air resistance. But recently, there's question on you release the ball, but now you're supposed to sketch the velocity time graph when there's presence of air resistance. So this video, we're going to focus on how do we draw that and what are the key things that we need to pay attention to in order to sketch the velocity time graph for each scenario. Now let's start with the first scenario where the ball is released from rest and then it bounces off from the ground. So firstly, we're going to consider when there's no air resistance. Now by convention, because the ball is going down initially, we will fix down as positive. So that means to say the initial part we will draw it on the positive section of the graph. So when you release the ball at time equals to 0, you know that the speed is 0 and the ball will start to fall vertically down, and as it falls, the speed increases. And you should know, because there's no air resistance, the moment you let go of your hand, the acceleration will be 10 meter per second square. That's acceleration due to gravity, and throughout it will be this constant acceleration. Now, let's assume to be more realistic, when the ball hits the ground, there will be a point where the ball is in contact with the ground for a short duration. It compresses before it bounces off. So having said that, so the ball, you know that it will never return back to its original position because some of the energy of the ball has been transferred mechanically to internal store of the ball and the surrounding, and also by propagation of mechanical sound wave to the surrounding. So the ball will only reach at a height that's smaller than the height that is being released. So let this height here be h1 and this height here be h2. So h1 will be greater than h2. These are things that you should know. Next, let's start to plot or sketch the graph. So initially, as mentioned, at time equals to 0, the speed will be 0. So we will start from the origin here. Now, then more importantly, as the ball is falling, let's draw the free body diagram of the ball. It is moving downwards, and the force that's acting on the ball right now is weight. W equals to mg, and that's basically the only force, and that will be the net force. So if I were to show it this way, the net force will be the weight W, and ma equals to your weight is mg, therefore your a will be your g, which is 10 meter per second square throughout. All right, so for a velocity time curve, you know that if it's constant acceleration, it should be a straight line with constant gradient. And let's give it some value here. So to make things easier, let's assume this is 2 seconds, just it will reach the ground. And what is the speed? You should know it should be 20 meter per second, because acceleration of 10 meter per second square means every second, 1 second, the speed will increase by 10 meter per second. So 1 second later will be 10, 2 seconds later, there'll be an increment of another 10, so the final speed will be 20. Next, as mentioned, there'll be there's a short duration where the ball is in contact during the impact. So to be more realistic, there will be a sudden drop in the speed, so there will be a short duration and then it continues on. So at this point, okay, that's where the ball hits the ground, suddenly comes to a complete rest, and then the ball is being compressed, and then just before it rebounds back, this will be your speed. But what is the speed? Either they will give it to you, so not to worry, but you know that definitely it will be less than 20 meter per second when it rebounds back, because as mentioned, some of the energy in a way is wasted, so the kinetic energy of the ball here will be lesser. So the speed in which it leaves the ground will be lower than the speed just before it hit the ground. So as it goes up here, same thing. Let's draw the free body diagram of the ball. The ball is going up, but the only force that's acting on the ball, which is its weight, is opposite to the motion. So your net force acting on the ball will be minus negative weight. Because why negative? Because the weight is opposite to the motion. So your ma equals to your minus mg. Your acceleration right now will be minus 10 meter per second square. So in other words, the ball as it is going up is decelerating, and it's a constant 10. So that means to say you have to make sure that you draw a straight line with constant gradient. And since you know the gradient here of a velocity time graph is the acceleration and is 10, and this is also 10, so these two lines must be parallel. Now another thing you may be wondering is, how do I know what time will it reach the highest point? Now in general, not to worry so much about this. Either they will give it to you, they'll provide, or they just ask you to sketch a rough sketch on the graph will do. But one thing you do need to know is, of course, it will be less than maybe the 4 seconds over here. It will take a less than 4 seconds to reach the highest point. Next, let's talk about the height in which you drop the ball h1. And in this graph, as you know, the area underneath the graph for velocity time curve represent the distance, in this case the height. This will be the area of the triangle h1. But take note of this is from here until here. All right, this is the area that will be the height h1. Do not include this triangle because that's the moment it hits the ground and the ball is being compressed. So do not include this small area here, this small triangle. Likewise for h2, h2 is from here, and I'm referring to this triangle. All right, so that will be your h2, and you know the area of h2 will be smaller than h1. Now I hope you're very clear with how do you sketch your velocity time graph when there's no air resistance. Next, we are going to consider when there is air resistance. Now, for example, if the ball is relatively light, that's where air resistance will come into play, or the ball is bigger in size because of the surface area, there will be air resistance. So when you first release the ball, it's the same thing. When the time is 0, the speed will be 0, and the initial acceleration, the moment you let go of the ball, the acceleration will be 10. So if you understand that, the initial part, the gradient is almost identical to the previous one. Next, as the ball is falling, same thing, the speed will increase. But the thing is, the acceleration will no longer be a constant 10. Let's draw the free body diagram again, but now with the presence of air resistance. You know air resistance will be opposing the motion. The ball is going down, the air resistance will be upwards. So how do you find your net force? It will be your weight minus your air resistance. Next, something very important, as the ball is falling downwards, the speed increases, and you know that your speed is related to your air resistance. The faster you go, the higher the air resistance. So that means as the ball is falling down, the speed increases, air resistance keep on increasing, and the weight is constant. So that means to say the net force is always decreasing. The magnitude of the net force is decreasing, and since net force is ma, your acceleration will be decreasing. And to draw decreasing acceleration on the velocity time curve, you should know that it's not a straight line anymore. It will be curved, and it curves downwards like that. The gradient gets less and less steep. And there are two things that you need to take note of. Because there's air resistance now opposing the motion, the speed just before it hit the ground will be lesser than 20. It will be lesser than that. And another thing to take note is the area underneath the graph over here, just when it hit the ground, this area must be equals to the area here, because the height that the ball is released, it is still the same. Next, just like previously, assuming there's a slight delay, a short duration where the ball is in contact with the ground, so there will be a diagonal straight line here where the ball goes to suddenly goes to zero and then before it rebounds back. Now, one thing also, the speed where it rebounds back will be lesser. Now let's consider the last section as the ball is going up. Let's draw the free body diagram. So the ball is going upwards, but the weight is acting downwards, and also the air resistance is acting downwards because it's opposing the ball that's going upwards. So F net now will be minus your weight plus your air resistance. As mentioned, why is it negative? Because the net force, which is the sum of air resistance and weight, is downwards opposite to the motion. And because of that, it will cause the ball to slow down, decelerate as it goes higher and higher until it reaches the maximum height. But one thing you should know that because the starting speed when it rebounds is smaller and the energy is lesser, so the ball will not reach the original height. Just like the ball in red here, it will reach at a smaller height, let it be h3. So what kind of deceleration will it be? As mentioned, when the ball is going upwards, the speed decreases. And if speed decreases, the air resistance acting on the ball will also decrease. So since the weight is constant, plus the air resistance that is getting smaller and smaller, the overall magnitude of the net force is getting smaller. And just using F net equals to minus MA, why negative? Because the net force is opposite direction. Since the overall net force is smaller, the negative acceleration will be decreasing. In other words, your deceleration is decreasing. And to sketch that on the graph, it will be a curve and the gradient will get less and less steep, and then until it reach speed velocity 0, that means it goes to the highest height over here. Now, of course, once again, you will not need to know what is the exact time that it reaches the highest point at this point here. Most probably, I mean, if they want, they will give it to you, then you just sketch exactly at this timing. Maybe we should just label the graph. This is point A when you release the ball. Point B is when it's just about to reach the ground before impact. And then point C is when it leaves the ground. And then point D is the highest point. So it will correspond to A here, B, and C. Now when it leaves the floor, the speed is the maximum and it's the maximum negative. Why negative? Because velocity is a vector quantity. The direction is opposite to when it's coming down, therefore is negative. And then as it goes up, the speed is getting less and less negative, meaning it's slowing down. So when there's air resistance, this will be your point A, point B just before it hit, point C when it rebounds, and point D, that's the highest height that it goes. So it will correspond to A, B, C, and D over here. So I hope you have a better understanding how to sketch the graph when there's air resistance, focusing more on the how you draw the shape. It's curved and the maximum speed will be lower and the rebound speed will be slightly smaller, and especially this part it should be a decreasing deceleration, so it will curve this way. Now whether what time it reaches the highest point, okay, like I say, it's not so important. If they want you to plot correctly, they'll give you the value, then you just follow. All right.